Love visa. For the sake of extension, Coulomb's law. That gives us the force experienced by a point charge because of the other charge. Taking that, we standardize the expression for the field at a point because of a point charge. E bar, right? Suppose there is a point charge of q coulombs and at a point P. Having the position with respect to the point at which charge is placed equal to R bar, the electric field intensity vector E bar at that point is Q by 4 pi epsilon mod R bar whole cubed into R bar is what we saw. This is the electric field intensity at the point of observation P due to a charge Q. The superposition principle here says what? If there are charges Q1 at point 1, point charges only, Q2 at point 2, Qn at point N, the electric field intensity at a point P that has the position vectors R1 bar from P1, R2 bar from P2, so on from Rn bar from Pn. The electric field intensity at the point of interest is a resultant of or the superposition of the electric field intensity at that point due to each charge Q I, because of which the electric field intensity E bar at that point is sigma summation I is equal to 1 to N. Please look at it. Qi divided by 4 pi epsilon mod Ri bar whole cubed into Ri bar. Please check it. In practice, the charges that we see are distributed charges, not point charges. Or distributed charges, not point charges. Using the electric field intensity at a point because of a point charge kept at some other point, and the mathematical tool, namely the integration, we need to determine the expression for the electric field intensity at a point because of a distributed charge. Distributed charges. These charges can be line charges in which charges distributed on a line. Surface charges in which charges distributed on a surface. 3. Volume charges in which charge is distributed in a volume. Any of these distributed charges of finite dimensions that we can see contain infinitely many, uncountably infinitely many point charges. They are the combination of. Any line charge is composed of infinitely many, infinitesimally small differential line charges. Any surface charge consists of infinitely many, infinitesimally small, tiny differential surface charges, and volume charges consist of similar differential volume charges. When you say the charge is distributed on a line and a surface or volume, the distribution may be uniform or may not be uniform, or maybe it is uniform or not. General distribution is non-uniform. Whenever we want to determine the field at a point because of these charges, we define something called as charge density. If it is a line charge, rho L is the charge density defined at any point on the line, as limit delta Q tending to 0, delta Q by delta L. So delta L tending to 0, sorry. In the differential length at any point on the line, at any point, we need to consider a differential length, see the charge delta Q in the differential length, and say delta Q by delta L as the line charge density. Line charge density. If it is a surface charge, rho S is the charge density given as limit delta S tending to 0, delta Q by delta S. And if it is a volume charge, rho V equal to limit delta V tending to 0, delta Q by delta V. Given a line charge with the charge density at any point, right? X, Y, Z in Cartesian coordinate systems, rho phi Z in cylindrical coordinate systems, and r theta phi in spherical coordinate systems. They are defined at any point on the line or surface on the volume, on the charge. Listen carefully. The electric field intensity at some point because of a line charge. At some point because of a line charge is what? Differential electric field intensity dE bar on a line. It is small dl at a general point that have the charge rho l times dl. Suppose this is the point of interest where I want to determine the electric field intensity because of this line charge. At any point, we consider the line charge element, which is the point charge of charge rho l dl. Define the general vector r bar from any point to the fixed point. Please concentrate now. Let x naught, y naught, z naught be the point where I want to determine the electric field intensity for the sake of talking about it. Cartesian coordinates. X, y, z is the general point on the line, because normally we defined lines mathematically as the relation between x, y, z, in which only one of the variables is independent, is what we saw. At any point x, y, z, if you fix x, y and z are fixed, because equation basically gives that. dE bar is what we talk about. Please concentrate here. This is what is important for you. Differential electric field intensity at the point of interest dE bar is equal to rho l dl. Listen carefully. When you talk about this dl, if it is there along a line parallel to x-axis or x-axis itself, at any x dx, dl is dx. At any y it is dy. At any z it is dz. At any point in xy plane it is dx ax plus dy ay. Root of dx square plus dy squared. Correct? No. That dl we saw is different along this line only, depending upon where it is. Rho l dl is a charge by 4 pi epsilon. Then r bar divided by mod r bar whole cubed. It's r cap. Correct? R bar divided by mod r bar whole cubed. And this E bar is equal to total E bar is the sum of the electric field intensities at the point of interest because of all infinitely many infinitesimally small line charge elements on this line. Because it is a summation under limit having infinitely many terms, in which the position is just moved through dl distances, I say that it is integral along a line, single integral, rho l dl r bar divided by 4 pi epsilon into mod r bar whole cubed. Let us now consider a sequence of line charges first. Number one, a line charge of length L along Z axis from minus L by 2 to plus L by 2 a point on y-axis which is there at a distance of y naught. This is the origin. If rho L is the charge density, line charge of finite length. Now, one point we should know, I will be adding a term hypothetical. Hypothetical means just considering it as a case for mathematics. It is impossible for us to have a line charge of finite length which is uniformly charged throughout. Because once you have a line charge of finite length charged, the charge will not reside on the line, but it will go to the tips and then stay as a dipole. Hypothetical. If I consider a charge configuration, please don't think whether it really exists or not. It is a case considered for us to understand the mathematical processes. Along z-axis, you have a line charge. Please concentrate now. To determine the electric field intensity at the point considered P, which is at a distance y naught from the origin on y-axis. Because we know the field at any point because of a point charge only, consider a small element along z-axis at any z. Please consider, understand the process. Address is at any z dz length. At any z dz. Dz is the length. Rho L dz is the differential line charge. At any 0, 0, z, because it is there on the z-axis. This vector r bar is equal to what in this case? R bar is equal to, because this is having the coordinates of 0, y naught, 0. This, the position is 0, 0, general z. The vector from 0, 0, z to 0, y naught, 0 is what? 0 ax, no x component. Y naught ay plus, no, minus, correct? Minus z az. You agree this? At any point on the line charge. And dE bar. dE bar is equal to what? The charge magnitude is rho L dz, because I know the charge per unit length as rho L. It is uniformly charged. Positional coordinate will not come here. Rho L dz. Z is a variable of integration for us, because the line charge is there along z-axis in which only z can change. X and y are zeros. Rho L dz by 4 pi epsilon into y naught ay minus z az by y naught squared plus z square whole power 3 by 2. If I want to determine the total electric field intensity, differential charge can create only differential field. Whenever I say that dz tends to 0, dE bar also tends to 0, it's a vector of tending to 0 magnitude. When I try to integrate, we see that there are two components. E bar is equal to rho L constant in this particular case by 4 pi epsilon. Integral minus L by 2 to plus L by 2, because Z varies from minus L by 2 to plus L by 2. Y naught dz divided by y naught square plus z square whole power 3 by 2 ay plus integral again minus L by 2 to plus L by 2, minus it is actually, z by y naught square plus z square whole power 3 by 2 dz. One point is that the expression in the integral corresponding to the y component is even function of z evaluated over the symmetrical limits, because of which we have to evaluate it. But the expression in the integral for the z component is having z in the numerator, because of which it is odd function. It is odd function, integral of which is 0. Now carefully say this. Here it is fine. But what I need to understand is, while integrating the expression for the electric field intensity at the point P, I should have considered such elements everywhere from minus L by 2 to plus L by 2. We considered one element at a distance z. Basically, when the z coordinate of the point is z, I would have considered in the course of integration an element which is at minus z from the origin. I know that from the discrete point charges discussion that we had, these two symmetrically situated charges will create two forces which aid each other along y-axis and cancel the vertical component of the other. One cancelling the vertical component of the field because of the other. Because it is symmetry of the distribution of the charge along z-axis with respect to the foot of the perpendicular dropped from the point of interest onto the z-axis, this integral is 0. For sure, because it is z by y naught squared by plus z squared over symmetrical limits, it is 0. And my physical understanding also says that this z component ultimately will not be there. At any point on y-axis. Listen carefully. So we have to now say that there will be only y component, and that y component can be obtained by integration, where we substitute for z is equal to y naught tan theta. Z is equal to y naught tan theta. dz is equal to y naught secant square theta d theta. Tan inverse limits from rho L by 4 pi epsilon integral minus L by 2 is minus tan inverse of L by 2 y naught, correct, to plus tan inverse of L by 2 y naught y naught squared secant square theta d theta. Already y naught is there. Dz is giving me one more y naught divided by y naught cubed secant cubed theta. One of the standard integrals that you are supposed to know for the sake of this subject. Becomes rho L by 4 pi epsilon naught or epsilon, depending upon the medium, y naught cos theta d theta. 1 by secant theta cos theta d theta is sin theta. Sin theta. I will call this as theta 2. I'll call this as theta 1 minus theta 1. Theta 1 to theta 2. Please check it now. Theta 1 to theta 2. Or it is actually minus theta to theta 1 to plus theta 1. Whatever it is. I should express the final result in terms of the known fields. No, theta is not given to me. Given quantity is not theta. I have to put ultimately the expression in the Cartesian system of units, where I can put x, y, z, whatever I want. Right? Ultimately, y naught and the length are the two things apart from the charge density that they have given. My substitution itself told me that z is equal to y naught tan theta, or this theta is equal to theta is this, tan theta is ay is finally we'll put, don't worry about ay now when we are discussing about the limits. L by 2 y naught, L by 2 y naught, correct? L by 2 y naught. What is sin theta now? So sin theta from theta 1 to theta 2 is actually what? Rho L by 4 pi epsilon y naught sin theta 1 to sin theta 2, right? Or I'll just put it, if this is not clear to you. Rho L by 4 pi epsilon y naught, given that tan theta is equal to z by y naught, sin theta is z by root of z square plus y naught squared from minus L by 2 to plus L by 2, if you don't understand it that way, is equal to rho L by 2 pi epsilon y naught, right, into L by 2 divided by root of L squared by 4 plus y naught squared. Check it. For upper limit, if z is equal to L by 2, lower limit minus of z is equal to minus L by 2, because of which it is 2. I can write it, no, now. Ay is equal to rho L by 2 pi epsilon y naught into L by root of L square plus 4y naught squared. Can I put it like that? Because we should be naturally comfortable with mathematics, integration and all. I always say that writing this step is crucial for us. And then this formula. Formulate the integral. Done. The remaining thing is easy for us. There are one particular thing is important for us, because in that case the field will have cylindrical symmetry. If the line charge is of infinite length, now the special case, if L tends to infinity, what is that I would have given here? In the integral only, I would have put minus infinity to plus infinity. When it is z is equal to y naught tan theta, theta goes from minus pi by 2 to plus pi by 2. In the integral, ultimately sin theta from minus pi by 2 to plus pi by 2 is 2. Or if it is symmetrically distributed about the foot of the perpendicular along z axis, and it is of infinite length, I should get the expression as the limiting case of this expression. L tends to infinity. If L tends to infinity, what will happen? This expression becomes equal to 1. Agreed? L tends to infinity because this is 1 by L by L root of 1 plus 4y naught squared by L. L gets cancelled out. Now L is equal to infinity will make this is equal to 0. 1 by 1 is equal to 1. If L tends to infinity, it is rho L by 2 pi epsilon y naught, the distance Ay. Extremely important case for us. Again to tell you, for any length we can get. Ultimately, what is it? You just look at this distribution, form the integral, put the appropriate limits. That's all. This expression is valid for all L. Listen carefully. Look at this expression. I will consider a case where there is a line charge of length L. This is y-axis, y naught. Line charge is there from 0 to L. In this particular case, also, you have to consider the differential line element at any z of length dz, because of which the charge on it is rho L dz. Again, talk about the radius vector from 0, 0, z to 0, y naught 0. But here, The only thing that we should know is what? Because the charge is not symmetrically distributed about the foot of the perpendicular dropped from the point of interest onto the line, the z component of the field will not get cancelled out. I need to evaluate both the integrals. The electric field intensity, this is true for this also. dE bar is true for that expression, that case also. But when I talk about E bar, what is E bar for this? Can you tell me? Rho L by 4 pi epsilon integral 0 to L y naught dz by y naught square plus z square whole power 3 by 2 dz az ay plus integral 0 to L z dz from y naught square plus z square whole power 3 by 2 dz az. We have to evaluate even this. Correct? Even though it is an odd function, my limits of integration are not symmetrical. I need to evaluate this with the tan substitution. Z is equal to y naught tan theta. I need to evaluate this with y naught square plus z squared is equal to t. 2z dz is equal to dt. Z dz is dt by 2. Correct? We need to integrate both y and z component because we know that z component is not getting cancelled out in this particular case. The third case in this. If I have a line charge of length L, distributed along z axis from minus L by 4 to 3L by 4, length is L. This is again y naught. What does that have to do? One is rho L by 4 pi epsilon y naught. Y naught is there. Rho L by 4 pi epsilon. No, y naught here. Into integral minus L by 4 to 3L by 4 because y component is because of all the elements considered. What is that y component expression? Y naught dz by y naught square plus z square whole power 3 by 2 ay plus when I consider the z component, whatever is there as the charge from minus L by 4 to plus L by 4, that the part is symmetrically distributed about the foot of the perpendicular. Z component, residual Z component is only because of the charge from L by 4 to 3L by 4, Z component. Z dz by y naught square plus z square whole power 3 by 2 az. Please check it.